Okay, so this video is going to be about initial theta data. So this is this description of this kind of massive tuple of information. Okay, so let's talk about this. So recall. So first, I want to talk about the Fricken involution. This is going to be helpful in describing initial theta evolution. This is going to be helpful. So we're going to start a little chapter on this. So recall. Crap. So recall that so here y0L is the curve. I say curve because it's not really a curve. Well, there is a curve, but this is I'm gonna talk about the stack. Parametrizing pairs E C. Okay, where okay, so I'm going to take this, these are going to be L points, so where E is an elliptic curve, over L. Okay, so here we're really taking, so here we're taking here EC in Y naught L L. Okay. So this is going to be the stack. So this is an elliptic curve over L, and C. This is what we want to happen. So C of L is a subset of E L L bar, cyclic of order L, stable under, oh man, that's bad, under stable, I'm sorry, I'm so slow, G of L bar over L. Okay, so this is what we want. This is how we should think about this. Okay, so there's some technicalities here. So really, when we plug in a scheme S, we're really looking at so curved, or these C's that are subschemes of E of L. They're finite flat subgroup schemes, which are all locally isomorphic to the constant the constant scheme, constant group scheme Z mod L. Also, the other thing to add is that this is not really a scheme. These pairs have automorphisms. So if I take the involution here, then this thing's going to be fixed, and that shows that there's kind of some fixed points here. So I think Brian Conrad has and James Parson has a good. I mean, there's a lot of places where you can see this, but there's some good notes that Brian has on his webpage from one of his old Vigor projects. Okay, so this is what we have. This is what anyway, we're just going to proceed like this. Okay, so now the Fricken involution. All right, so the Fricken involution. Okay, is going to be mapped from here to here. So it's given by, okay, EM maps to E mod M, and then we take the torsion, mod out by M, and this is going to be equal to, and then we're going to define this. This is going to be defined to be equal to E underline M underline. Okay, so this is the Fricken involution. Okay, so this is something we have, and so note in this definition that okay, so elliptic curve. Well, I'm not going to write that down. So so elliptic curves. Well, maybe I will actually. So, oh crap. So so elliptic curves are automatically principally polarized. So we can take the dual isogeny. Okay, so if f is our isogeny in the Fricken involution, given by okay, so let's just, we already said what it was given by. This is the Fricken involution. Then note that we have the following. Then we have the dual isogeny. So E bar mod M bar. So this is E mod M mod EL mod M, like so. And so this is just E mod EL, which is E. Okay, this is because the co-kernel of so the co-kernel of multiplication by L is just E itself. Okay, so one can also see, right? See that E underline L mod M underline is isomorphic to M. Okay, so this is a via duality. Okay, so this is a little bit harder to see. Okay, so I just wanted to refresh on this like little quotient construction here before I get into the definition of initial theta data, which I'm going to do now. Okay, so let's do initial theta data. Okay, so let's fix the following. So let F be a number field. Okay, let E be an elliptic curve. Over F. And we're going to let K be equal to F adjoin the L torsion here for L is a fixed prime. So L is a fixed prime. Okay, and we're going to take this thing. So this is also going to be equal to, we could also say this is F bar, and then we'll take the kernel of rho L. So this is an alternative description here. So in this description here, let me just switch. So in this description here, so rho L is this Galois representation, the mod L here, EL F bar, and so this is so after choosing a basis, this is contained in GL2 FL, since EL F bar is isomorphic to let's say FL squared. Okay, so All right. Okay, so this is what we have. And so the kernel of this map defines a subgroup here. The fixed field of this is also going to be the torsion. Okay? So we're going to fix EM in y naught of k, and some element here. Okay, so here an element of E underline L. So some element of the L torsion here. A generator. Okay, so we're going to fix these things. So we have F, E, L, this M, and this epsilon. Okay. So let's give the definition. So we will say EM, this dude L, like this, sits inside initial theta data. Okay, if and only if the following holds. 1, so we're going to demand that F over Q JE is Galois. And the image of rho L GF, this is going to be a subset of the automorphisms of EL F bar, contains a subgroup isomorphic to SL2FL with respect to some basis. So this, for example, rules out the elliptic curve having complex multiplication, because the image of this Galois representation will be abelian if it has complex multiplication, and this is not an abelian group. Okay, so we're going to demand that the square root of -1 is an F. We're going to demand that EF contain, let's say, for safety purposes, EF bar 6. So the 6. Let's say the 30 torsion. Okay, so let me make a little note here. Is that in IUT? So a little note is that in IUT1, the assumption is 6 torsion. In IUT4, in the application, he switches to 30 torsion. Okay, so third property. So we're going to have 6 properties altogether. Okay, so there exists a non-empty set S, subset of VQJE of bad non-Archimedean places for the curve for E over QJE. Okay, so with odd residue characteristic. So in this thing, you're allowed to omit a bunch of bad places. Okay, so you just need one. So for example, on the curve E11A1, the favorite elliptic curve of everybody, there's one bad place. So it's defined over Q. There's one bad place at 11, and it has multiplicative reduction. So you could just use that single thing. For other elliptic curves, you could just like take your favorite place, and then all the stuff would apply. If you just picked one place, one bad place, if it was provided it wasn't two. Okay, so now there's a bunch of conditions on L. So L does not divide the residue characteristic of bad places. So these are the bad non-archetypal. So these are the bad places. Residue characteristic of bad places. L does not divide the order of the tape parameter. Tape parameters at bad places. L needs to be bigger than or equal to 5. I was looking at my notes here real quick. So L needs so this is so what is this? So this is at let me just say this. So order of tape parameters at bad places of V of F over S. Okay, so these are tape parameters at bad places of V of F over S. Okay, and L, finally, 1, 2, 3, L does not divide the degree of F over the field of moduli. Okay, so there's these 4 conditions. We have 2 more. Okay, so then there's condition 5 and 6. Okay, so these 2 things are going to be technical conditions. Well, not so technical. Relating the torsion, so local and global torsion. So local at bad places and global torsion, and this involving this generator and M. Okay. Okay. And so this condition. Okay. So let me just. I'll come back to this condition here because it's important. But let me first say that this is what it is. I'm gonna say this one. Okay. Then I'll come back to this definition. But first we'll just give a definition. So a collection let's say F bar over F, X over F, L, let's call this M underline, and then we'll say V underline. Okay, so this involves also V underline and V underline. So that was that section there. S, sometimes this thing is called V bad mod, and epsilon. Okay, this thing will be defined up to plus or minus 1, is what Mochzuki calls initial theta data. Okay, so there's a series of reductions he goes through about saying you know, that this thing, this thing can be determined by, so here, sorry, I didn't say what XF is. So XF, so this is EF, and then we're going to remove 0F. So we remove this 0 section. So this is, so we removed the 0 section of our elliptic curve. Okay, that's an algebraic closure. I already said that. Okay. So let's go and let me just go and talk about the rest of this technical conditions, and I'll come back to this. Okay.